Find the limit, if it exists, of the function 2xy divided by the quantity 2x squared plus y squared as xy approaches 0, 0. And one technique for getting a feel for whether or not the limit of a function exists is to graph the function. And if it's a complicated function, you can use technology to graph it. And what you want to do, so we're going to graph this function as f of xy. And what you want to do is look at the output values of the function, the height values of the function, for input values x and y near 0, 0. So I've already graphed this, and I get a picture that looks like this. So that's the surface in red. And if you look near input values of 0, 0, you can, even at this kind of zoomed out distance, you can see some funny business going on here. So let's zoom in, see if it looks any better. And it really doesn't. If you look at it, there's a jaggedness to the surface for input values near 0, 0. It's hard to tell exactly what the output would be for an input near 0, 0. So I'm actually thinking when you get this strange wiggly behavior like this, oftentimes it indicates that the limit doesn't exist. And actually, you can reinforce that line of thinking by approaching 0, 0 from two different paths and then looking at the function height values. So let's think about the path y equals x. So you can see that positive y values are up here, positive x values to the right. The line y equals x runs like so. And if you look along that line, except for values near 0, 0, the height seems to be relatively constant. The output values seem to be a relatively constant height on that line, somewhere between 0.5 and 1. However, if you approach, say, on the line given by y equals 0, so the x-axis, looks like we get different outputs. Looks like a height of 0 for the function on that line, no matter if you approach from positive x values or, in other words, from the right or from the left, where x values are negative. Looks like you get a height of 0. So two different limiting values on just two different paths, that's enough to say the limit doesn't exist. But, of course, the graph doesn't tell us for sure. We don't know what's really happening in here. So you can't say for sure based on a graph that the limit doesn't exist. But that's what we suspect at this point. Okay, let's make a table of function values for this function to get more evidence that that limit doesn't exist. I'm going to use Excel. It's a spreadsheet program, comes with Microsoft Word, to plug in numerical inputs to the function and look at the outputs as these inputs get close to 0. So here's how you do that. Let's go to A1, punch in a 1, go to cell A2, punch in another 1, go to cell A3. Here's where we punch in our formula for the actual function. Now A1 is going to be acting like x, and A2 will be acting like y. So the formula will look like this: 2 times x, which is A1, times y, which is A2. That's the numerator, divided by parenthesis, left parenthesis. 2 times x is 2 times A1, and then you have to square that, plus, so that's the same as having 2 times x squared in the denominator, plus y is A2 squared. So you got to square the y also. And so that's the equivalent of our formula, with A1 and A2 taking the place of x and y respectively. So get off that cell, either using the arrow or the mouse, and you'll see 0.6 repeated. Now, now that the formula is inputted, we want to input some actual function input values. We'll put x values down the side here and y values across the top. So let's do, let's start at negative 0.2, go to negative 0.5, 1.5, how about we'll go by 0.05. And then highlight those two input values, pull down on the lower right-hand cell, and Excel will extend the pattern to you. We'll go all the way to x equals positive 0.2. And then across the top to the right of the 0.6 repeated, the 2/3 essentially, let's put in the same input values for y values. So negative 1.5. Actually, we'll start at negative 0.2, and then go to negative 0.15, and then again highlight those cells, pull in the lower right hand end of the last cell, and have the spreadsheet extend the pattern all the way to 0.2, and then highlight everything below and to the right of the inputs, and as well as the 0.666 blah blah blah. Highlight everything except the 1 and the 1, and then go to data and what if analysis, and then data table, and then make the row input cell, it has to be actually A2 to get this right, and then A1 for the column input, and hit OK. And this looks good. Let's go ahead and highlight our inputs, maybe in bold, and maybe color them green. And let's see, bold and green. So we can tell the difference between our inputs and outputs, and maybe even make the outputs a different color. There we go. So here's our table. The tan or brown color, whatever color that is, would be the function height values given the input values in green. So as you can see, when x and y are the same, no matter which values we look at, we get a height value that's between 0.5 and 1. It looks like it's about two. It looks like it's going to be 2/3 if you computed it by hand. Whereas if you approached 0, 0 via y equals 0 along here, you get height values of 0, except at the function itself, because you'd get division by 0 if you plug in y equals 0. So two different limiting values, apparently at least, following two different paths. So more evidence that this limit does not exist. But it's not enough evidence, because you'd have to check all the numbers if you did it this way along the paths. So how do we actually show that the limit doesn't exist? Well, we'll do that next. So let's show that this limit doesn't exist. I'm going to take two paths to 0, 0. So imagine approaching, you're in the xy plane, you're flat, you're a two-dimensional point in the xy plane, and you're approaching 0, 0. One direction you could approach is along the line y equals x. So one path you could take to 0, 0 is the path on the line y equals x. And if that's the case, then this limit changes. This guy right here changes to x. And so we get the limit of xy, the limit of 2xy divided by 2x squared plus y squared, rather. As xy approaches 0, 0, this limit becomes the limit as xx approaches 0, 0. And that changes this numerator to 2 times x, or 2x squared, and this denominator to 2x squared plus another x squared, because again, y is equal to x, which is 3x squared. And we have this sort of cancellation. Keep in mind, we never allow both coordinates to become 0, 0. So we don't get a division by 0 there. We get 2/3 essentially. You know, and that's with the caveat that x, y is never actually, they're never both equal to 0, right? Okay, so that's one limit value on one path. Now, let's take the path, how about y equals 0? Which means the above limit becomes the limit as x0 approaches 0, 0 of 2x times, well, okay, if we think about it, if we plug in 0 here for y, we get 2x times 0 over 2x squared plus 0 squared. 2x squared times 0 over 2x squared plus 0 squared, which is just the limit as x0 approaches 0, 0 of, okay, you get 0 in the numerator divided by 2x squared, which is just equal to 0 as long as, you know, x doesn't equal 0, which is the same thing as saying as long as both x and y don't equal 0, 0. So we get two different limit values for two different paths to the point 0, 0 in the xy plane. So we could say this. So two paths to 0, 0 yield two different limiting values. I'll say two different values for the limit. Which means that original limit does not exist. D and E for does not exist. Now keep in mind, you can only use this technique to show that a limit does not exist. You can never use it to show that a limit does exist. Because even if you get the same limiting value on 2 or 3 or a million different paths, you have to show that it's the same on all paths. So you can't use this technique to show that a limit does exist, only that it doesn't.